Hi everybody, so this is my second lesson on atomic spectra, so watch this after the previous one, which was about the emission and absorption spectra and just an introduction to Bohr's model of the atom. So according to Bohr, he said that the electron can occupy different energy levels outside the nucleus. The energy level closest to the nucleus is called the ground state, and each energy level is given a number which is called the quantum number, or the energy level number, and it's represented by the letter n, the little n. So the n equals 1 is your ground state, okay, and that's the lowest energy level. Now the thing is, the energy of an electron that's bound to the atom is actually negative, and you wonder, how can something have negative energy? The thing is, when the electron has zero energy, it can actually leave the atom, and if it has more than zero, then it will actually have kinetic energy to go outside, okay, to be released. And so that's what we call the ionization energy. So Bohr came up with a formula to calculate the energy of the electron at each of these different energy levels. And he started off with the generalized formula for calculating the wavelength. So the wavelength of any of these emission absorption spectra of any of this light that's given off is 1 over lambda is equal to r, which is Rydberg's constant, times 1 over s squared minus 1 over l squared. Now we know that there's a connection between wavelength and frequency. So the frequency is given by speed of light over wavelength, or the same formula becomes c times r over 1 over s squared minus 1 over l squared. Now when an electron jumps from one energy level to the other, it's going to absorb a photon of a particular amount of energy, and this is just, it can only occupy those discrete energy levels. An electron cannot occupy any space in between, okay? So the energy of the photon that's either absorbed for it to jump higher, or a photon that's emitted when it drops to a lower energy level, is given by E equals hf. So this formula becomes hcr, because you add the h as well, times 1 over s squared minus 1 over l squared. Now this is the energy of a photon that's either emitted or absorbed, okay? Now, so if you expand this, the energy of a photon that's either absorbed or given out is given by hcr over h squared over chr, or hcr over l squared. Okay, and the energy of an electron at any level, where n stands for any level, is given by negative c hr over n squared, where n stands for whatever energy level it is. Now just to elaborate on what is c, h and r. So c is the speed of light times 10 to the power of 8 meters per second squared. H is what we call Planck's constant, and R is Rydberg's constant. So that's what the C, H and R stand for. And if you want to calculate what is the energy of the electron at the ground state, at the lowest energy level, all that you do is just multiply these three numbers, because you're dividing it by 1 squared. So what you get is 3 exponent 8 times 6.626 exponent negative 34 times 1.097 exponent 7, and you end up with 2.18 times 10 to the power of negative 18 joules. It's actually a negative number. So when n is equal to 1, the energy of the electron is negative 2.18 times 10 to the power of negative 18 joules. Okay, so I'm going to rub the board, and I'm just going to show you what happens just to calculate the energy of the electron at different energy levels. So I'm just going to rub this. So what I'm drawing is a central nucleus, and these are the different energy levels. So this is my nucleus at the center. This is n equals 1, n equals 2, n equals 3, n equals 4, and I've also kind of drawn an n equals 5. Okay, so suppose you have an electron at the lowest energy level, and in order to jump to the highest energy level, or this is not the highest is infinity, it can leave the atom, but let's say it jumps from energy level 1 to energy level 5, it has to actually absorb a photon of energy. So the squiggly line represents a photon which it has to absorb, and the energy of the photon is h times f. And the energy of that photon should match the energy of that level. So in order to jump from this lower energy to the higher, it has to absorb a photon of energy. When it's at that higher state, it's what we call in an excited state. It doesn't stay there for too long. It drops to a lower level. So if it drops to level 2, so if it drops from there to level 2, no matter where the drop is, any drops to level 2, the part of the spectrum, the emission spectrum, is always visible light. That's why you've got the 2 squared for Balmer's formula. Any drops to level 1, that is the biggest jump. So the biggest jump is when you have the most energy given out. So the most energy, the ultraviolet has got a higher frequency, therefore higher energy. So the most energy is all drops to level 1, and that's your Lyman series. And any drops to level 3 or 4 is all in the infrared series. There's another way of representing this diagram. So instead of drawing it as circles, it's quite nice to draw it horizontally. So this is your lowest energy level, and then you've got your next one, n equals 2, and you've got your n equals 3, n equals 4. Now if you notice, these lines are not evenly spaced, because if you calculate the energy of your lowest when n equals 1, this is negative 2.18 times 10 to the power of negative 18 joules. In order to calculate the energy of quantum level 2, I just have to divide this answer by 4, which is 2 squared. Okay, so if I divide that by 4, I get 0.545 times 10 to the power of negative 18 joules. Okay, it's a negative number. And then in order to get what's the energy of energy level 3, so I just go 2.18 exponent negative 18 divided by 9, because 3 squared is 9, and I get negative 0.25, it's a 24, 0.242 times 10 to the power of negative 18 joules. Okay, and then if I need what's the energy level for 2.18 exponent negative 18 divided by 4 times 4, 16, I get, this is 0.136 times 10 to the power of negative 18. So can you see? So this is, if you had like a graded thing, that's the biggest drop. So any drops to level 1, these are your biggest drops, and all these are in the Lyman series. Okay, any drops to level 2, they are all in the visible spectrum. This is your Balmer series. Now the important thing is, the biggest drop to level 2 is much smaller than the smallest drop to level 1. I'm going to extend the slide. So this is a much bigger drop compared to this. Okay, that is why each series is quite distinct. And then any drops to level 3 is in the infrared part of the spectrum. So this is your passion series and so on. Okay, again, the biggest drop to level 3 will be much smaller than the smallest drop to level 2. And that's why the infrared is quite distinct from the visible light. And the visible light is quite distinct from your ultraviolet light. And that is why in that formula, all drops to level 1. So when it all drops to level 1, that is why your S is 1 for Lyman, 2 for Bama, 3 for passion, and so on. So I hope that makes sense. And this is to do with your spectral lines. So bye for now.